So far, we've looked at a single wave or pulse propagating through some medium and looked at its characteristics. Many interesting wave phenomena in nature, however, involve multiple waves or pulses interacting with each other. Such phenomena can only be analyzed by considering the collective effect of many traveling waves. Understanding of such phenomena can be achieved through the aid of the superposition principle. When two waves meet, they interact and superimpose or add to make a new wave. Each wave disturbance is caused by a restoring force in the medium. Since force is a vector, then the forces from the two waves add up vectorially. This means that the waves can add to create a bigger wave, or they can cancel each other out. This phenomenon is called superposition. Superposition is a vector sum of two or more waves at any position and instant in time. A direct consequence of the superposition principle is that two traveling waves can pass through each other without being destroyed or even altered, like in the case of the two water surface waves shown here. The expanding circular surface waves do not seem to destroy each other, but they appear to overlap and in the process produce a complex pattern that can be viewed as two independent sets of expanding circles. Likewise, when two sounds from two sources move through the air, they pass through each other, but the resulting sound that one hears at a given point and moment is a collective combination of both sounds. This principle has been effectively utilized in applications like noise-canceling headphones. A simple visual representation of the superposition principle can be shown when considering two pulses traveling in opposite directions on a stretched cord. For simplicity, these pulses will have the same shape, the same amplitude, and moving with the same speed. In both cases, the displacement of the medium is in the positive y direction. We can represent the pulse with a mathematical expression given by y1 and y2 being some function of position and time. These functions describe the shape, the speed, and the direction of the pulses. Note that y2 moves in the opposite direction to y1. The red line represents both pulses when moving simultaneously on a single chord. When the wave pulses begin to overlap, the resulting complex waveform is given by simply adding the corresponding wave equations so that y net is equal to y1 plus y2. When the crests of the two pulses coincide, they produce a symmetric waveform of double the amplitude. The two pulses finally separate and continue moving in their original direction, with the two waveforms remaining unchanged, as if the two pulses had never met. Let's now consider the two pulses again, except one is inverted. The pulse in the upper blue line displaces each point of the chord along the positive y direction, while the pulse in the lower blue line displaces each point of the chord along the negative y direction. The red line again represents both pulses when moving simultaneously on the same chord. When the wave pulses begin to overlap, the resulting complex waveform can be mathematically represented by simply subtracting the corresponding wave equations so that y net is equal to y1 minus y2. When the crests of the two pulses coincide, the algebraic sum of the two displacements result in zero amplitude. It's as if the two waves have cancelled each other out, but only momentarily. As soon as the two pulses separate from each other, they continue to move in their original direction, with the two waveforms remaining completely unchanged, as if the two pulses had never met. Another term used to describe combining waves is called interference. For the two pulses shown here, where the displacement of the medium is in the positive y direction for both wave pulses, we saw that the resultant waveform exhibited a displacement greater than those of the individual pulses. We refer to that phenomenon as constructive interference. In this scenario, where the two pulses are displacing the medium in opposite directions along the y-axis, the resultant waveform exhibits a displacement that reduces or cancels out. We refer to this superposition as destructive interference. While pure constructive and pure destructive interference do occur, they require precisely aligned identical waves like those shown in the animation. The superposition of most waves produce a combination of constructive and destructive interference and can vary from place to place and time to time. Sound from a stereo, for example, can be loud in one spot and quiet in another. Varying loudness means that the sound waves act partially constructively and partially destructively at different locations. Let's now consider the two pulses shown in the following animation and identify which statements are true. What would you say about these two pulses? When the two pulses overlap, what different type of interference will take place? In summary, if two or more traveling waves are moving through a medium and interact, the resultant wave function at any point is the algebraic sum of the wave functions of the individual waves at that moment in time. This is known as the superposition principle or interference. Constructive interference occurs when two waves are superimposed in phase to create a bigger wave, while destructive interference occurs when two waves are superimposed out of phase to create a smaller wave.